So welcome back to the PowerPoint slides. This image is a 3D plot of the real half-hourly data that we've just extracted. So I'll show you how to do this in a few slides, but just wanted to get an overall impression of the data produced. So along this axis, we start from 1st of January 21 all the way to the 31st of the 12th 21, and along this axis, or the depth axis, we start at midnight, midday, all the way through to midnight. So what you can see here is the peaks and troughs of the actual consumption, and what you can notice is some significant spikes through the summer. So this spike, and we'll see a bit better angle, but this spike is around July, and we have a August spike here. And from speaking with the actual owner of the business, or the owner of the golf club, these are significant social events. So when you're looking at half-hourly data, you always need to speak to the people operating the business to understand what's going on. You can say to them, oh, there's something unusual happening in July, and they come back and say, well, that's when we had our big golf weekend or golf week, where there was an awful lot of activity and frankly nighttime social events. So this was when catering, and similarly as we get to the end of the year, it's a venue for Christmas parties. So again, as you would expect, a lot of energy use. Also, we have a bit of a trough here, and this is a part of, unfortunately, a COVID lockdown. So what you can see here is the golf club was effectively closed for a number of weeks, and that reflects a early year COVID lockdown in 21. So these are the real operational issues associated with a typical business plot. Now, what we're going to do is, this golf club wants to apply significant solar because they have a spare area. So this is a half-hourly representation of solar generation. And again, I'll show some more detail around this, but this is inverted because consumption is a positive number and generation is a negative, simply because when we add the two together, you're obviously netting off generation with consumption. And this curve reflects solar. So what you can see here is peak generation is in the summer months, June, July, August, at midday. So there's no generation at night, which is obvious for solar, and also limited generation in the winter months. So it maximizes solar generation in the summer months. In the winter, so up until March, and then from October, November, there's limited generation from solar, and that's just natural. It's the number of hours of sunlight in a day, and it's also the relative angle of the sun in the sky. So a little bit more detail on how those graphs were generated. We have a time of day profile, typical time of day profile. So we start at 5:30, 6:30, we begin to generate some solar to a maximum peak at midday, and then similarly, and then it obviously tails off where we drop off by 18:30. But similarly, we have a time of year profile, and the net profile is a combination of simply generation time of day, generation time of year, and that gives us the 3D plot we saw previously. So maximum power output midday in July, minimum power at night, which is obvious. So looking at some of the data in terms of the red, amber, green, this is the consumption of the business from the 1st of January. So this is a flat version of the 3D graph that we saw. And again, you can see here in March to April, the COVID dip or COVID lockdown dip. Here again, we have the spikes for the summer social parties. And as we get to the winter, we have frankly higher energy use because there is some electric heating on this site, but also these are the nighttime socials again coming through. And we've divided into green, amber, red into the GWOS charges. So you can see the proportion of red charges, fast bulk or amber charges. So that's between 7 a.m. and 11 or 11:30 p.m. Remember, red being between 4 p.m. and 7 p.m. And then we have green, which is effectively nighttime, midnight to 7 a.m. And we have a rather large base load. So in terms of energy efficiency, you'd be looking at, well, what is this? You know, because the golf club would be closed between midnight and 7 a.m. What is this base load of electricity use? It is in fact, you know, fridges, compressors, IT, security, any number of systems. But, you know, that's where you would first look at, well, has something been left on that could be switched off overnight? Some of the fridges, certainly the drinks coolers, could be switched off overnight without having too great an impact on the coldness of the beverage. So that's where you start looking for energy efficiency with half-hourly data. So solar generation. So this golf club, we're considering a ground-mounted solar of potentially 250 kilowatt capacity or potential power, which broadly equals 243 kilowatt hours per year. So just as a rule of thumb, you know, if you have a 100 kilowatt system, you'd expect 100,000 kilowatt hours out of it. Depends on where you are in the world and the radiant energy, but that sort of 1 kilowatt to 1,000 kilowatt hours is nominally a rule of thumb for solar generation. So again, you can see the profile that according to amber. So naturally there is no green generation because green is effectively nighttime. So the bulk of the generation from solar occurs in the amber periods, and this would be typically between the morning into early afternoon. But also we have some red generation, which is good because bear in mind that the cost of electricity during the red period can be twice as much for this particular charge as the amber period or orange period. So any solar generation in the red is excellent or very good. That's what you want to see, really. So with this generation and this consumption, adding them together, so bear in mind we have negative here, consumption is a positive number, so adding the negative to the positive, we have this chart. And what you can see before is a significant chunk of the amber and lesser extent of red, but still some red, has been removed from the input. So your new import consumption looks like this. The green is virtually the same. Just bear in mind that the scale has slightly changed. So we're at 600 at the middle of the chart. 600 is now up here. So if we look at the green, that let's say between 100 and 200, so that holds through, that the green has not been affected by the solar generation, and also the I'll say the winter usage has had minimal effect on the amber period. The big chunk obviously reflects the curve of the solar generation, and our final graph here is the actual exports with solar. And what you can see here is the significant nature of the export. So for this particular business, the issue is, well, hang on, is the solar generation too much? Is it too big? Can the local grid handle the export of that amount of solar generation? And it's exporting 153,000 kilowatt hours, 153,656 kilowatt hours here. That is a lot of export.